Hello everyone, my name is Ishan. So today I wanted to talk about this very interesting and wonderful topic of the wavelets. So first of all, what are wavelets? So wavelets are basically small wave-like oscillations which satisfy certain criteria. So more formally, to define a wavelet, it has to satisfy the following criterion. So it has to have this integral from minus infinity to infinity psi of t dt to be 0 and this criterion. So what exactly does this mean intuitively? So let me explain this with the help of an example. So if we consider, for example, this wavelet, for instance. So what makes this a wavelet? Why is this so special? This might seem like initially a random bunch of wiggles, but as we will see, this is a very special type of waveform. So it satisfies the criterion that when you draw the time axis and when you draw the amplitude axis, it turns out that the areas above the x-axis and below the x-axis perfectly cancel. So that is the property of zero mean, meaning the average, like if you take all the time instances of the signal, it will come out to become 0. And the second criterion basically tells me, like, say if you take any waveform like a sine wave or a cosine wave, it's infinite, right? It's going on forever. You don't know when it's going to end. I mean, unless someone tells you that it's for a fixed duration. But in reality, those are periodic waveforms and they repeat infinitely. But a wavelet is a finite waveform. We are only having it for a finite duration. So this integral that we had here is basically telling me my energy is going to be finite. Now why is it energy? Because the magnitude square represents our energy. Energy is a scalar quantity. I mean, not exactly a scalar quantity, but you can say it's a square of a magnitude. So it's going to be it's going to be representing the energy, and it must, and therefore because it's less than infinity, it must be finite. And in your sinusoidal signal, your energy is not finite, because if you look at the value of that integral, it's going to have, when you square it, basically what happens to the waveform, you're basically taking all the negative parts also above the x-axis, so you get a positive kind of waveform. Of course it will be amplified due to the squaring, so that will all sum up, and that will be, because integral is basically a sum, it will all add up and it will become an infinite thing. It will tend to infinity. But in your wavelet, that it tends to 0. So that is your energy signal property and your zero mean property. Now, why in the first place are we introducing wavelets? What makes wavelets so special? Like why do you need wavelets? Well, as it turns out, wavelets, the idea of wavelets wasn't always there. Like, you started out with many different methods of analysis. So let's just take a short detour and explain how wavelets came about. So you have time domain, like you can give any random signal. Here I'm considering an analog signal, of course. You have amplitude and you have time. This is your x of t. So this is any continuous time signal, and this is basically your time domain. And now you have try to represent there is this field of something called as Fourier domain analysis. So you would take the Fourier transform of any continuous time analog signal and you would convert it into frequency domain. So what appears as a totally random waveform would become sort of like peaks or impulses in your frequency domain. So of course your y-axis will still be your magnitude or strength, but here the magnitude would actually be the strength of the frequency components. So this would appear as peaks. Now, why am I explaining this? So now, when you're looking at a signal, you're observing the signal in your continuous time domain. Can you say anything about the frequencies? No, you cannot. You don't know anything about the frequencies. You can't say that there's a one, like for example, if I give you the sine t plus 8 sine 3t plus sine 8t, and it's going to look something like this. It's going to look completely random. It's going to look like this. Like it would look something like this. So just by looking at a time domain plot, can you tell that omega equals 1, 3, 8? No, you cannot. But when you go to the frequency domain, you will see impulses 1, 3, 8. Now in your frequency domain, you will be able to tell, okay, 1, 3, 8 are the frequencies. Wonderful. But you won't be able to tell what the original time signal looked like. Could be any signal. So here is where comes in the concept of time frequency resolution. It basically tells me if there are close enough frequencies, like say 100, like 1 hertz. I have a 1 hertz frequency signal, and then I have a 2 hertz frequency signal, just double, or even say not even 2 hertz, say 1.5, just a little bit greater. To tell these frequencies apart for sure, you need to look at them for a particular period of time, and that is intuitively what you call your time frequency resolution. And there is of course much more deeper mathematical connection, but here I'm only going to explain it intuitively as to how it arises for our purposes. So basically, in your time domain analysis, you have perfect time resolution, but you can't tell anything about the frequency. So I'm going to represent the time frequency resolution as a grid for better gaining a visual understanding of this concept. And your frequency resolution will be perfect. You'll be able to tell whatever frequencies are there, but again, I don't know anything about the time. Perfect time resolution. Perfect frequency resolution. Now, as scientists always do, they try to solve this problem. And a person called Gabor came up with a way to take a compromise between the two. So he came up with this way of doing a time frequency analysis. So basically he said, why rather than taking perfect time resolution or frequency resolution, I'll take a compromise. I'll take something in between. Like I'll take some. It's fine. I'll lose some time resolution. I'll lose some frequency resolution, but at least I'll have a bit of both. So that is where the concept of windowing comes in. Windowing is basically like an observer's glass. You are literally looking at the signal for particular durations of time. So if I have any random signal like this, and I introduce a function, like a window does not mean necessarily a rectangular window. It could be any function. Just wanted to make that clear. So in general purposes, and the most popular one is of course is the Hahn window. So basically what you would do is you would take this window and then you would examine particular segments of time period in order of milliseconds, and then you would analyze that signal for milliseconds, and that would give you something called a spectrogram. That would be the time frequency, and that would be what you would do. This windowing would basically tell you the property of the signal, like basically the frequencies how the frequencies evolve over that time. Like when you multiply the signal, like let me explain it in this way. When you take the Fourier transform, you get x of omega into x of t e to the minus j omega t dt. But here I'm also multiplying my signal with an additional window. I'm multiplying it with an additional window because I want to make my because in the original Fourier analysis my sinusoids were infinite, right? So basically what I'm doing here is I'm localizing my sinusoids with an additional window function by multiplying it, because real signals are not infinite, we all know that they're finite. So we want only for that particular duration. That's why we multiply it with this. So then you would multiply it with this, and then you would get something like this. So it would become, so only this part of the peak would be visible. Of course it would be like weakened by that magnitude of that multiplied by that, but this part would become 0. This would become 0 while this peak was visible. So that is basically what happens. You take a window, you take the signal at particular instances, you basically take overlapping windows because you don't want to lose content signal. Let me just draw it here with more clarity. So you would take windows like this. Let's draw the window in different color. So then that would give you this content, and so on. And just to represent the time frequency resolution here too, it would be actually, because the window is fixed, it would be an evenly spaced grid. So everywhere my window size is same and my window function is same. So I would get an evenly spaced grid, which basically what is that telling me? It in relation to time frequency resolution is that our resolution is fixed. Time frequency resolution is fixed. So now this is the major shortcoming of our windowing and our whole short time Fourier transform, as they call it. But what is just windowing and then taking particular instances for which the signal is mostly similar, you could say. Now this is where our wavelets come in. The major property of wavelets, which I forgot to introduce, was that I will not have a fixed time frequency resolution. Now you may ask, why in wavelets I won't have a fixed time frequency resolution? It's because in the original, if we go to the original wavelet here, psi of t is only the mother wavelet. It's actually a family of functions that satisfy these criteria. The actual wavelet actually is dependent wholly upon this equation. So basically I can have copies of the same wavelet, but it would be squeezed and stretched. So it's basically, if you take the same wavelet as earlier, like this for instance, I can squeeze it, I can stretch it, I can do anything with it, and that is wholly dependent upon our factor A. If my A is greater than 1, I would of course get a stretched version. If I got A less than 1, I would get a compressed version. It would be compressed. And B is the same thing. B is the same thing that we were doing in windowing. I'm shifting and I'm applying it. whatever, it's the same, it's serving the same purpose as our top, so there is nothing different from that. Now the big advantage of varying your the big advantage of the squeezing and shifting is, now my window isn't fixed. So whenever I want to get a better understanding of time, I can of course whenever I want better understanding of transients, as in high peaks or better like short periods of time, I can take this wavelet. Or if I want a better understanding of the how long something goes, then I can take the stretched version. Meaning if I want better frequency resolution, this is better, and this is better for better time resolution. Because I'm able to observe it for longer. Here I'm not able to observe it for that long. And now that has a cascading effect on our whole spectrogram. Instead of an evenly spaced grid, I now have a rectangular grid, and that grid actually is not evenly spaced anymore. I can decide how big each box needs to be. So instead, earlier we were restricted to only have a particular time frequency resolution depending upon our window choice. Now I am able to decide based on when I want to know how the signal, when I want to have a better understanding of its time properties, or when I want to have a better understanding of its frequency properties, basically. So if I take this here earlier, now I can have 4 here, or I can have even more here, or the number of boxes here. And now this is called a scalogram. Of course I'm just drawing this plot as a rough plot, mostly just to understand time frequency resolution. So what this means is, this has a this now does something really wonderful for us, because now my time frequency resolution is no longer fixed. That basically means I can now choose when I want to capture high peaks, when I want to capture sustained oscillation. So when I want to see more harmonious sounds, I'll take a more stretched out wavelet, and if I want a more capturing the peaks, I'll take a more compressed wavelet, basically. And of course the duration also will be considered. That's solely dependent upon how much you compress it and stretch the wavelet, basically. So our whole purpose here is to keep time frequency resolution as minimum as possible, and get our best understanding of both the time and frequency characteristics without too much compromise. And now getting to the part of speech. So why does this matter to speech? Why the hell does time frequency resolution matter to speech? Why is it so special? Why is it so important? Well, speech is a very complicated signal actually. So it's a non-stationary signal. And what does non-stationary mean? Well, non-stationary basically means that your amplitude of the signal is random. It can be anything. You can't predict with certainty what it will be at any moment of time. So it could have a sudden burst, or it could have a sudden drop, or I could just have a high harmonic oscillation then a burst. So basically that's what the signal is telling me. Now Traditional Fourier analysis fails very badly at this, because simply because I cannot tell you what frequencies are there, as I mentioned before, and your short time, your windowing can only tell you your frequencies at a particular time with a fixed accuracy, or with a accuracy that is not great, but it'll tell you, and it'll be fixed simply because your time frequency resolution is fixed. That is basically like your least count in a way, your minimum uncertainty. Like that's the minimum you can go. So because of that, wavelets are very good at capturing transients. And what are transients? Fast changing oscillation, something that's very like changing over time, which is not really a constant with respect to time. And for this, it's not we use a very specialized type of wavelets. I mean, there are many wavelets. Then there are many wavelets. Like for example, you have the Debussys, which looks something like this, and then you have your Haar wavelet, you have your Shannon wavelet. I'm just giving a few examples just to get an idea that it's not just that one wavelet. And the earlier one that I've been using for demonstration purposes is actually known as the Morlet wavelet. It's actually a complex wavelet, which we're not going to discuss here. Now, for our purposes in speech, Debussys and simplets and coiflets are the most used. Now, why, you may ask? Well, as it turns out, the A actually comes in powers of 2. Now, most people would ask, or a valid question is, why powers of 2? Well, let's talk about digital storage then. All your bits are in powers of 2. Your number of possibilities, possible combinations are all in powers of 2. And that is where your Debussy simplets excel. Naturally, that power of 2 concept is embedded within its very properties. So it is excellent for storage purposes. So rather than in Morlet, where A can take any value, as in it could be a decimal, it could be an integer, fraction, whatever, basically any real value. Here I am capturing it in powers of 2. So I am able to efficiently capture information in this grid better. Here I have to waste more time storing other values of A that are not even useful for my signal. Store values of A. Naturally already embedded in it. And that makes the Debussy simplets ideal for hardware implementations, or even something as widely used as MP3 compression, because I'm able to efficiently pack information in a less dense, and maybe you can even say less dense or less spacious grid, because bits are 0 and 1, and those are 2 possibilities, and each bit is 2 possibilities. So that exactly is the whole summary of wavelets and why wavelets are crucial for speech or any kind of analysis. And you cannot do speech without doing wavelets or having an understanding of why it is so widely used. This clearly sums up why we need wavelets. So well, that sums up my um my introduction of wavelets, or my justification of why wavelets are required in speech. I hope I was able to give a better, more intuitive understanding of this topic, and thank you to you all for listening. Bye bye.